you, Jeff, for the awesome introduction, and thank you, who was it, making the introduction video? That was awesome. That was like my once-in-a-lifetime chance of standing together with Emmanuel Miranda. Okay, now let's switch gear and talk about planets and planet formation. Now we're seeing the familiar ones on the stage right now, not to scale, the solar system planets. So the inner part, we can see 4 rocky planets, and further out from the central star, we can see 4 giant planets. And as we're standing here now, we actually know a lot more about planets than just those 8 in our own solar system. We know, because of Kepler, we know, does it work? Okay. More than 5,000 planets orbiting around other stars that's not our own sun. And we can find some of the planet system just look like our own, like this one, with smaller planets closer to the central star and bigger ones outside. And some of them look pretty weird to our own eyes, like this one, with a really big planet close in to the central star. Okay, that's enough. So we ask the question, why? How are they formed in the first place? So to answer that question, we'll need to go back in time and find the fundamental ingredients to make those planets. And we need to figure out a recipe and see what kind of physical mechanism that decide what kinds of planets get to be formed. And eventually, magic happened, boom, we got the planet. So everything starts here in giant molecular clouds. Now we're seeing a really famous one is a star-forming cloud in Orion constellation. You can see it in winter sky from here. And if you look into those white boxes, the small ones here, you're seeing cocoons illuminated by newly formed young stars within them. And within those cocoons, right around the newly formed star, there are typically accretion disks around them, and within those disks, that's where planets are formed. So now we have our ingredients. So planets are formed out of materials in the disk that's 99% of hydrogen molecule, only 1% of dust. So if you want to have planets like our Earth, like a rocky planet, it turns out there are a lot of work that needs to be done. Turns out the dust particles in the polar planetary disks we just saw are only in micron size, so that's only 1/100th of the diameter of our hair. And they have to grow into rocks, into boulders, into planetesimal's, and eventually into a planet of thousands of kilometers in size. So it turns out for small dust particles, it's very easy for them to grow. They'll just stick together and make dust bunnies. But at some point, as you might imagine, if you throw 2 rocks at each other, they do not like stick together and become a big one, right? They bounce or they smash into each other. They do not grow anymore. So that's the first barrier we hit in the process of planet formation. And to be honest, astronomers don't know exactly how to overcome those kind of barriers, and that's only one of them. There are more to come, but they have hypotheses. So one hypothesis is saying having icy grains and icy rocks could be helpful. Just like here on Earth, about a certain altitude, snow and ice stay on the ground all year round. And in the polar planetary disk, if we go further away from the central star, the temperature drops. So gases like hydrogen and carbon monoxide are able to freeze out on the grain surface. Now we have sticky grains. So what happens is, if we have 2 rocks that's covered with ice hit each other, that's more like 2 snowballs colliding to each other. When they collide, the ice on the surface will melt a little bit, and that gets sticky. So it's much easier to glue 2 rocks together that way. So rocks could potentially grow larger in size into boulders. And other hypotheses suggest maybe one rock will somehow just get lucky and grow into much bigger size. That's the lucky one hypothesis. And a rock can grow large enough for gravity to take over. That's another stage for planet formation. So gravity is a really strong force that's only important for very, very massive things. So dust grains have to grow into roughly boulder size for gravity to be useful in grabbing things and focusing things together. There are other hypotheses saying maybe we can somehow create a very stable pocket in those protoplanetary disks where rocks can pile up together and that could somehow grow into larger bodies. Anyway, we don't know. Somehow magic happens and we do have rocky planets around other stars. And the process I described is actually not efficient to form planets like Jupiter or giant planets around the star. So for that to happen, we have another idea. This is called gravitational instability, where instability simply means collapse. So what happens here is a protoplanetary disk can get so heavy that it cannot support itself anymore. So it starts to collapse into itself. Now we have baby planets formed, just like the formation of stars, and they will create spiral arms around them, and that will help to clear out the disk and helps the evolution of the system. So I've talked about pretty pictures, but that all happens in the theorist's mind. Those were simulations. In reality, planet formation happens in the dark and is surrounded by dust. And because materials is not very hot, so a typical temperature in the protoplanetary disk is a few tens of Kelvin. So that's about minus 300 Fahrenheit. And things do not glow very much at that low temperature. So it's really hard to see those things in optical wavelengths. But we do have options. So with radio telescopes like this particular one is called ALMA. It's located in the Atacama Desert in Chile. And this telescope works in sub-millimeter and millimeter. So that's a radio wavelength that's slightly longer than the wavelength using your microwave oven. So with a telescope like this, doesn't work. We can see the glow of dust because they are really luminous in longer wavelengths. And this is an actual observation taken by the ALMA telescope you just seen before. And the name of the disk is HL Tau. Astronomers pointed the telescope to this disk because they thought it's going to be really boring. This is a really young disk. It's just too early for planet formation to happen. But they saw this. So we're seeing a lot of rings. We're seeing the dust emission. So those are really gaps potentially opened by planets in those disks, or dust grains growing into larger bodies, so they're no longer visible in the wavelengths that we're seeing. And with radio telescopes, we can also see the dance of molecules. By dancing, I mean it literally. So when molecules in space, they can vibrate and they can rotate. And when they vibrate or rotate from one energy level to the other, they emit their chemical signatures, like their chemical footprint, and you can identify them by taking a spectrum. So now we're seeing a sugar molecule. This is, I think, an artist's illustration around a solar-type star. And then this is the spectrum, that's the peak. This is exciting news for me just because sugar is something really fundamental for the emergence of life. So we've seen like basic ingredients for life way before even the planet was formed. And a new exciting telescope that's going to come online is this one, James Webb Space Telescope. And this picture was taken, I believe, a couple of years ago here in Austin during South by Southwest. We had a real-size model on the auditorium shore. And this telescope works in the infrared, where we can see the vibration of molecules. And that will take us to the surface of the planet-forming disk. And we'll be able to find more complicated molecules and potential ingredients for biological life. So I'll leave the picture here and take questions. Thank you.
Alright, thank you very much, MC Snowline. We've got time for some questions, and I'm going to go with Alan since you're waving at me.
Yeah, I think that's the reference on this slide. Will the slides be put online at some point?
Are you talking about the Kepler? Is that the one you mean? The one with all the planets going around the stars? Yeah, it's on YouTube.
Yeah, it's on YouTube. It's made by Dan Fergecki. I think that was the one made in 2013. That's the up-to-date one. And Adam Krause actually, a year ago in his Astronomy on Tap 1, showed the previous version of this movie. Uh-huh. So
can you repeat the question?
Yeah. The question was: is there a particular kind of star that's likely to have disks around it? Actually, that question specifically was a nomenclature question. So it turns out every star has, or at least had, a protoplanetary disk around it at some point. So yeah.
Okay, more questions. One towards the back and the middle here.
So, is there a difference between the creation of rocky planets, like the ones we have in the inner solar system, and dwarf planets?
Sorry, I didn't quite hear the question. So you're asking, is there any differences between the rocky planets and
dwarf planets? Yeah.
Dwarf planets. Are you referring to brown dwarfs or like dwarf planets like in our own solar system?
Second one.
I see. So those are, we think of them more like, I wouldn't say failure. Those are more like bigger planetesimals. So in the picture I talked about first, that's the core equation picture. Basically, that's a bottom-up pathway for planet growth. So basically, you start from smaller dust grains that make rocks, make boulders, make planetesimals. And planetesimal is sort of the milestone for rocky planet formation. They're about a few kilometers in size. And then, if there's enough material for them to get together and grow bigger, there could be rocky planets. If there isn't enough material around there, in the neighborhood, then they could end up becoming a dwarf planet. Does it make sense?
Okay, more questions for MC Snowline. I see one on the aisle back here.
We were talking about how there were no idea how the rocks were not couldn't get together because they kept smashing together.
Yeah.
But you did before, like bumping because the relative velocities of everything. This is
Yeah, that's a great question. So the question was, I talked about rocks hitting each other and then bounce off, but like the relative velocity within the disk should be small enough, so maybe that wouldn't happen. So it turns out, yes, you're right. So it's a accretion disk. So the biggest component of the velocity is the capillary rotation, is the rotation velocity. It turns out because there is turbulence in the disk, and there's gravity that brings everything down into the midplane, the center of the disk. There is a certain degree of random velocity, and that's enough to break the rocks. So astronomers are not very sure about the degree of random velocity, so that's a parameter that people can play in simulations. But yeah, a lot of different things could happen, and what you mentioned is certainly a possibility.
Take a question from up here on the balcony.
What is the trigger for the formation of gas planets as opposed to rocky planets? Is there some sort of trigger event that promotes the development of a gas giant rather than, say, a rocky planet?
So the disk, the accretion disk, is supported by both the gas pressure, which is just the heating, because the gas has some random velocity and heat, and the rotation. And if the disk is heavy enough, it will simply collapse. And there is actually an equation to calculate this. So if the disk is massive enough compared to its rotational velocity and its temperature, then it's simply gonna collapse. So that could happen, for example, in the outer part of the disk, or that could happen simply around in more massive disks.
Okay, we've got time for one more question. Did I see one up on the second level? No, maybe a question already got answered. Okay, any more questions for MC Snowline? Down here?
Yeah, early in the talk you mentioned that bigger planets have smaller planets. What's your theory on that?
Yeah, that's another great question. Actually, I missed a really important component in this talk, which is migration. So it turns out planets move around after they're formed. So it turns out we found really big planets closer to the central star sometimes too, and the hypothesis is because if planets are formed when the disk is still around, planets will interact with the disk itself, and that force is enough to move the planet perhaps, either inwards or outward. So yeah, there are different ways of moving things around and forming things at different places. But then one basic idea is to make something big, you have to have a lot of materials to start with. So the idea of migration is popular because there's more material in the outer part of this just because there's more space. The density is dropping as you go further out, but then just because the space, the size of the ring is much bigger, so planets forms in the outer part of this will have more material to start with.
Okay, I'm going to say thank you very much to MC Snowline.